Okay, so welcome to the 25th lecture, and the topic for today is compactness in metric spaces. And before, we have established a very important characterization of compact spaces, is that compact is equivalent to limit point compact, which means that every infinite set has a limit point, and is equivalent to sequentially compact, which means that every sequence has a converging subsequence. And they're all equivalent. But now we're going to introduce another characterization of compactness using the completeness which we introduced last time. As we know that Cauchy sequences are bounded, so if X is compact, then X is complete, right? Because Cauchy sequences are bounded and X is compact, which is sequentially compact, right? If a sequentially compact, it has a converging subsequence, and because the sequence is Cauchy, so it must be complete. Okay, but completeness does not imply compactness. Just consider the very basic example, real number line, right? The reals. So we want to look for an extra condition A, such that completeness plus something is equivalent to compactness. So what is the condition A? And the fact is that this A is called totally boundedness. So we say a metric space is totally bounded if for any epsilon positive, there exists a finite covering of X by epsilon balls in X. Okay. And immediately we see that totally bounded is implies bounded, right? Because if you just cover X by 1/2 balls, finally many of 1/2 balls, then the diameter of X by the triangle inequality, we have this, right? But bounded does not imply totally bounded, right? Because if we consider the standard bounded metric on R, if we consider this metric on R, this is definitely bounded, right? Bounded by 1, right? Bounded by 1. By the definition here, right? It is bounded by 1. But it is not totally bounded for epsilon equals to 1/2. Because if it's epsilon equal to 1/2 less than 1, then d bar is going to be equal to d. So how can you cover R by finally many of 1/2 balls? It's definitely impossible, right? Thus, boundedness, totally bounded, is strictly stronger. Weaker. Weaker than bounded. Okay. So here we have a theorem that compactness is equivalent to complete and totally bounded. And for this direction, if it's compact, it's definitely complete, as we said before, and we have this, right? Since it's compact, right? This is open cover X, and X is compact, so we can reduce to finite, which we just have a covering of finite epsilon balls. So the hard part is the converse. Well, for the converse, suffices to show that X is sequentially compact. And so we want that for any sequence, we want a Cauchy subsequence, right? If it's Cauchy subsequence, because it is complete, right? If it's Cauchy, it's complete, so we have a converging subsequence, okay? So we just cover X by finite 1 balls. So one of the ball must contain infinitely many of X n's, right? So let J1 be all the n such that Xn is in B1. Now we again cover X by finitely many 1/2 balls. As J1 is infinite, so one of, like, say, B2 must contain infinitely many of Xn such that n is in J1, right? And we just define J2 be all the n in J1 such that Xn is in B2. So in general, given Jk, we can cover X by finitely many of 1/k plus 1 balls and define Jk plus 1 as the n's in Jk such that Xn is in Bk plus 1, where Bk plus 1 has radius. Radius is equal to 1/k plus 1. Okay, so we have constructed a collection of subsets of positive integers, the indices. So now we just pick 1 and 1 in J1, and for nk chosen, we can choose nk plus 1 such that it is larger than nk. This can be done because every jk plus 1 is infinite, right? Every jk plus 1 is infinite, and it is a chain, right? It is a decreasing chain. Thus, we have that if ij is largely equal to k, and I and j are all in jk, right? Because we have this. Okay, so this can be done because it's infinite, and this implies this is true, right? This and this is true. If this is true, which gives that x and 1, x and j are in bk, right? But bk has radius what? 1 over k, right? So this eventually shows that, well, it's a Cauchy sequence, right? This nk, k equals to 1. This is a Cauchy sequence. So we're done. Okay, so our main mission for this lecture is to relate to the case of the function spaces, continuous function spaces from x to Rn in the row bar metric, which is in the uniform metric. And we have a definition that given the metric space and f is a subcollection of the continuous functions from x to y, and x naught is in x, we say that this collection is equicontinuous at x naught if for any epsilon greater than 0 that exerts the neighborhood of x naught such that for any x and for any f in a collection we have this. Okay, so this is pretty strong. It's called equicontinuous, and we have a lemma that given initial conditions, all right, we say this collection if it's totally bounded under row bar, then it is equicontinuous. Okay, so we have a lemma. So let's just prove this lemma. And to prove this lemma just by triangle inequality. First, we just let epsilon between 0 and 1, and we let delta equals to epsilon over 3. Okay, so that, and we can cover f by finite many of delta balls because it's totally bounded, right? And we can make the balls, we can extend them in cxy. Okay. Because originally we have it is bounded on the row bar, but row bar is restricted on f, right? But now we can first we cover f by finding any delta balls on the row bar f, and then we can extend it in this, right? Which again, right, it's a covering of f. So we have those balls covers f. Each of them are continuous, right? So we can pick a neighborhood of x naught such that this works for all I, right? We just pick neighborhood for each, and then we take a finite intersection, which is a neighborhood, right? Open again, such that this is true. And we have that because this covers f, right? So for any little f, it must be in one of the balls. If it's in one of the balls, we just apply triangle inequality. For x and u, first we have d bar f and fi, right? So we have this is true, is because this, right? And this is true, is because fi is continuous, right? X and u, right? Such that this is true, right? This is because fi is continuous, and this is again, right, same reasoning. So we have these together, which means that by triangle inequality, with the distance between those, right? Because delta is less than 1, right? So we can just replace d bar by d, right? So we have this is true, so that f is equicontinuous, right? F is equicontinuous. Okay, and before that we have a definition that a sup metric, okay, define it on all the bounded functions, okay, all the bounded functions. We define it as equals to the sup metric between two functions is the supremum of the distances between f and g of x. And this definition makes sense, right? Because fx bounded, gx is bounded, then their union is also bounded. If this is also bounded, so this would make sense. Okay? Now, if X is compact, then rho is defined on this, right? So we can just define, okay, no. So if X is compact, then rho is also defined on it, right? Because f of X and Y is compact, right? This is compact. And Y is a metric space. Compact subspaces in metric spaces are bounded, right? Yes. Because for any fx that is compact, we fix any point x, right? And then we can just do like the increasing radii of balls, and by compactness, right, it must be like, it must contain one of the balls. So it will be explained this more detailed later, but as for now, you should be knowing that fx is compact and rho is defined on it, and then we have rho bar fg is equal to minimum of rho. So we have this relation, okay? This is not the definition, this is what we have, okay? Okay, so with this lemma, remember with this lemma, we have X space, metric space. If it's totally bounded, then it's equicontinuous. And now we have a partial converse of above lemma, is that if X and Y are both compact, then the converse holds. Okay? If Y is also compact, X and Y are, yes. So we have no definition of compactness, then we have this implies this. If we have X and Y are both compact, then the converse holds. If it's equicontinuous, then it's totally bounded. Okay, so this is the lemma. So it suffices to show under rho is true holds, right? Because it's bounded on the rho bar if it's totally bounded on the rho. Okay, so just think about this. So we just work with rho, we pick epsilon greater than 0, we pick delta is to epsilon over 3. Then, first of all, we pick a neighborhood that makes this equicontinuous. So we have neighborhood of A, such as blah, blah, blah. So X is compact. It can be written as a finite union of all such this. And we denote them as UI, okay? And also Y is compact, so we can cover Y by finitely many delta over 2 balls, right? Say 1 to m. Then we consider J, all the mappings from 1 to k to 1 to m, okay? Is all the function from 1 to k to 1 to m. And for each alpha and j, if there exists f such that f of ai belongs to v of alpha I for all I, then, so for each alpha and j, so alpha and j is a mapping from 1 to k to 1 to m. If for this mapping there exists an f in the collection such that f of ai, so remember ai is the finally of the points, right? The points. It maps the point into this alpha ith neighborhood, right? Alpha ith neighborhood for all of them, so it matches. Then we write such f as f alpha. Okay, so this f matches with alpha. Then the collection of all alpha that f alpha exists, right, is finite, because j prime, so all such alpha that has an f that matches with, we denote this subset of j as j prime, right? But j is finite, so j prime is also finite. So here what we have is really a finite collection in theory, right? But this collection makes sense because j prime is non-empty. Why is j prime non-empty? Because if you just pick any f, because they covers y, right? They covers y for any f because they covers y. So we can just say like f is equal to f alpha for some alpha and j, right? We can just first define something, right? We pick an f because it covers y, so j prime is definitely non-empty. Okay, so now we're gonna show that Okay, so this part shows that J prime is non-empty. And okay, so now suppose that this collection is given. Suppose this collection is given. We show that this collection is a covering of F. We see that it is epsilon balls, right? And it is finite, okay? And it's a covering of F. If we show this, then we're done. For F and F, first, right, there exists an alpha and J such that this is true because Y, though they covers Y, okay? And we claim that this F is in the epsilon ball of the F alpha for this corresponding alpha. Okay, so for X and X, for any X, it must be in some UI. If it in some UI, first we have this is because that it is equicontinuous, right? It is equicontinuous. It is equicontinuous. So this is because F is equicontinuous. And this is because we have this, right? F AI is in this, and F alpha AI is also in this, but those V alpha I are delta over 2 balls, okay? So their distance is less than delta over 2. And F alpha AI and F alpha X, right, their distance is less because they're equicontinuous, right? So these two are because F is equicontinuous, right? And this is because the V alpha I, right, is a delta over 2 ball. So from here we can just boom, 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 this with this, this with this, and this with this, right? With the triangle inequality, we have that their distance is less than wait a second. Okay, this is what is 2 plus 1 over 2 plus 1 over 2 is 2 over 5. Okay, so it's 5 over 2. Okay, so wait. 5 over 2 times 1 over 3. Yes, yeah, exactly. 6 over 5 epsilon. Okay, I'm not wrong. For any x, which means that the supremum must be less than or equal to this, which is strictly less than epsilon. So we're done. Right, so we're done. We have this is true, right? F and F alpha are epsilon close. So we're done. Done with the partial lemma. Okay, so we're gonna use them in the proof of the theorem Ascoli. The classical version of Ascoli's theorem. So here's the definition before that. Given the metric space, subcollection of the continuous function, we say this collection is pointwise bounded if for any alpha and x, f of alpha, which is the collection of all the outputs of f under f, is bounded under D. Pointwise, it is bounded. This collection is bounded. Okay, so here's a statement of Ascoli's theorem that given the compact space and the Euclidean space in either Euclidean metric or square metric, and the continuous function spaces from x to the Euclidean space in row bar metric, and then we let f be a subcollection, give it the subspace topology, right? This is a metric topology, row bar. Then the closure is compact if and only if it is equicontinuous and is pointwise bounded under D. Okay. So we have this equivalence. This is the Ascoli's theorem. The closure is compact if only if it's equicontinuous and is pointwise bounded under D. So we first let G denote the closure throughout, okay, through closure F and this throughout. Now, for this direction, suffices to show that G is equicontinuous and pointwise bounded because F is a subcollection of G. right? F is a sub-collection of G, so like, right, this is automatically true. Now, G is compact, which means that it's complete and totally bounded under the metric on it, all right? We have it at the beginning. If it's complete and totally bounded, it is equicontinuous, right? If you forgot the lemma, right? If it's totally bounded under this, it's equicontinuous. If it's totally bounded on the row bar metric, it is equicontinuous, okay? So it is totally bounded under the row bar metric on it, then it is equicontinuous, okay? And since we have this holds, right? So row and row bar gives the same topology on G, right? This is a theorem. We have it in metric spaces. So let me just find it. Metric topology section. Where is it? I think it's here. Right. Give me 1 second. Let me define it. Let me just find it. Yes, like this. Give it any arbitrary metric spaces, and we have this, the standard bounded metric. We have the topology they generated are the same, right? So in our case, because we have this, right, so they give the same topology. So if you're compact in this meaning, right, then you're also compact in like in this meaning, right, in this topology. And as I said, it is bounded. Compact are bounded. If you just consider the increasing balls for a fixed function, right, this is open, right, and since it's compact, it must contain in one of them, which is exactly 1, right, which is contained in a huge ball, which shows that it is bounded, right? Then, if it's bounded on the row, it is pointwise bounded under D. You think about this, okay? You should think about this. If it's bounded on a row, then it is pointwise bounded under D. I mean, this just follows by the definition of row and D, right? So, surprisingly, we're done, right? Because it's equicontinuous and it's pointwise bounded. To show the converse, so we want to show that if X is equicontinuous pointwise bounded under D1, we show that the closure is compact. Well, first we show that if F is equicontinuous pointwise bounded, then so does the closure G. Okay, and this is easy, right? If we just, for G and G, because it's in a closure, so we can just pick a function that is arbitrarily close to it, right? Arbitrarily close to it, and because F is equicontinuous, we can so does make G equicontinuous, just simply by this relation. Okay, and using the given condition F is equicontinuous. This is an exercise for you. Remember this. Okay, remember this. And I mean, row and row bar gives the same topology. So the neighborhood in row, like we can have another neighborhood in like in row bar and row. Row bar row is the same thing because they give the same topology. Okay. And for pointwise boundedness, for A and X, it is pointwise bounded. Okay, since it is pointwise bounded. Now for G and G prime, first we pick F and F prime such that F and G prime are distances are less than 1. We can make the diameter of G at A less than or equal to n plus 2, which is again by triangle inequality. So yeah, so does G is equicontinuous and pointwise bounded. Now, second, we show that there exists a compact subspace of Rn such that Gx, the union of all G of X, the image, the range, for all G and G is contained in Y. Okay, is contained in some compact subspace. Okay, and to show this, for A, first we pick a neighborhood such that it is equicontinuous, and we've seen this logic before, right? Because X is compact, right? So we can write it as a we have compactness of X, right? We have compactness of X, so we can write X as a finite union of the neighborhoods. Now, because G is pointwise bounded, right? They are all bounded, so the finite union of bounded sets is again bounded, right? So if they're bounded, then you must contain in some big ball center at the origin, right? But also UAI covers X, because UAI covers X, okay? UAI covers X, and UAR, they make GX and GAI, right? There are one distance less than 1. So from here, we see that GX is contained in this, right? For any G, right? This actually holds for any G, right? Because, okay, if for any G, then G of, say, X, right? G of X and we can relate it to G of AI, right? We can relate it to G of AI. And we just use triangle inequality because this is true, right? This is true. And we also have this is true, so that this is done. Because GX with 0, right, plus 0 with G of some AI, right? Oh, sorry. No, it's like for any distance between GX and 0 is less than or equal to the distance between GX and G of some AI plus, by triangle inequality, G of some AI and the 0, right? So this is less than 1 and this is less than n. So it's less than n plus 1, okay? Yes, exactly. So they're all contained in a ball. If you just take the closure, it's automatically compact. Right, so we're done. Okay? We've done the claim that this is true, there is a compact such that this is true. Now we show that G is compact. If we show this, we're done, right? First of all, G is complete, right? Because it is closed. The closure, like it is all closed. And Rn is complete, which means that the continuous function space is also complete, which shows that it's a closed subset of a complete space, which is complete. Okay? It is also totally bounded on the row, right? Because we have this for some Y compact, then G is actually a mapping, continuous mapping, collection of continuous mapping from X to Y, right? If you just restrict the range, it is still continuous, right? This is the idea, right? Because we have all the images are contained in Y, and restricting the range still gives continuity, right? So G is equicontinuous, right? Because by the lemma, right? G is by the lemma is totally bounded on a row, right? We're given that G is equicontinuous, and by the lemma, G is totally bounded on a row, right? So finally, it is complete and totally bounded. It's complete and it's totally bounded on the row, which is compact. Okay. Compact under row and row bar. Same thing, same topology. So I didn't specify under which because they give the same topology. Okay, so we have proved Ascoli's theorem. We proved Ascoli's theorem. And finally, we're going to characterize the compactness of subset of the continuous mapping. So the corollary is that the same setting, exact same setting, okay, then a subcollection of this, any subset of this is compact if only if it's closed, bounded. This is very familiar with the Heine-Borel theorem, right? It is closed and bounded with an extra condition that is equicontinuous under D. And this is equivalent to being compact. Okay, and this. Okay, so for this direction, if it's compact, it is bounded on a row, right? Compact is bounded on a row, so this is done. And it is compact, which means that it is complete and totally bounded on the row bar, right? But we only need completeness. F is complete, and we want to show that F is closed in this, right? Because to show that it's closed, we pick a point, a limit point, then we have a sequence that converges to this F. And this Fn is a sequence in F that is Cauchy, is complete, so Cauchy sequence converges. But by the uniqueness of limit, right? Uniqueness of limit that F is, in fact, lies in F. Unique is limit because in Hausdorff spaces, right? Limit metric spaces are Hausdorff spaces, and right, we're done. Thus, it is bounded and it is closed, right? It is, if it's closed, then it's equal to its closure, right? And we have, it is compact, right? It has a compact closure, which is, it is equicontinuous under D by Ascoli, right? By Ascoli. Right? If it's compact, then it is equicontinuous, right? So we're done. Compact is bounded on the row, we're done. Closed, we're done. Closed gives that it is equal to its closure, and we're given that it is compact, so it has a compact closure, so it is equicontinuous by Ascoli. Now for this direction, closed, bounded, equicontinuous. Okay, let's just, if it's closed, right, it's equal to its closure. And is bounded on the row, which means that it is pointwise bounded on the D. It is equicontinuous under D. So these two combine together by Ascoli, the compact closure, right? The closure is compact, but it is closed, so F is compact. And then we're done, right? So this is finally a characterization of compact spaces as a subspace of the continuous function space. Okay? All right, and this is everything, and I'll see you guys next time.